Hello, and welcome to my virtual presentation on the topic of industrial applications of swept source optical coherence tomography, or SS-OCT. In this presentation today, I'll be giving you a few minutes of background on OCT, how it's evolved over the past few decades, and how it works to generate 3D images. And then I'll provide some highlights on the use of this powerful technology in a handful of applications outside of the biomedical imaging fields where OCT has traditionally been used. OCT was originally pioneered by several academic groups in the early 90s. It evolved from a telecom test technique for inspecting optical fibers into a two-dimensional tomographic or cross-sectional imaging tool for assessing layered structures in biological tissue, such as the retina. As such, ophthalmology became the first commercial application for OCT in the late 90s, but it was largely a niche technology due to its relatively slow imaging speed. In the early to mid-2000s, an alternative system architecture called frequency domain OCT came about by advances in line-scan CCD arrays and in rapidly tuned or swept laser sources used in SS-OCT. This resulted in about 100 to 1,000-fold increase in imaging speed without any major trade-offs, and OCT became a technology capable of rapidly scanning 3D volumes. For the last decade, due in part to advances in commercialization of swept laser sources at Axsun, swept source OCT has gotten faster and capable of imaging wider and deeper fields of view, as well as with higher resolution and in smaller and more portable and robust packages. It's created opportunities in many other medical fields, as well as some exciting non-medical or industrial applications. Today, OCT is about 100,000 times faster than it was just 2 decades ago, and next-generation VCSEL-based swept sources continue to push the limits of speed and scanning range. OCT works by illuminating an object or sample with laser light and then collecting the backscattered light, usually via fiber optic, which then interferes with a reference beam. That interference signal is detected and digitized, and then spectral analysis is used to generate a profile of the backscattering intensity as a function of distance along the probing beam, in other words, along the depth into the sample. Then, depth profiles are acquired repeatedly as the probe beam is scanned laterally across the sample to create a 2D tomogram, and multiple tomograms can then be assembled into a 3-dimensional dataset as the beam is scanned across the 3rd dimension. There are various methods for beam scanning in OCT, but a common one shown here is based on a dual-axis galvo scanner and objective lens that create a flying spot or raster pattern in the XY dimensions, while the spectral analysis of the interference signal is generating the Z dimension. Other common scan geometries are helical or cylindrical in nature, such as when scanned by a rotating fiber optic inside a borescope. Ultimately, the 3D dataset can be represented as a point cloud, a series of cut planes, or reconstructed into a top-down view or volumetric rendering as shown here. You can appreciate in these sample images how OCT is able to characterize the thickness of multiple layers, including a thin conformal coating, as well as the metal and dielectric layers of a printed circuit board. The blue cursors on these 3 images indicate the perpendicular planes in which the other 2 images are sectioned. With any tomographic imaging technology, there is a trade-off between resolution, or the ability to see small features, and depth of penetration, or the ability to see deep into the sample of interest. OCT fills a niche between microscopy and ultrasound, with resolution on the order of a few to 10 microns, and penetration depending largely on the transparency of the material, but usually in the range of 1 to 10 millimeters. Of course, metal is an exception where penetration is 0, and OCT can provide only topographic information. Unlike some competing modalities, OCT is non-contact and non-ionizing, and can be delivered via fiber optic into harsh environments from relatively portable and robust system hardware. Finally, since OCT is a coherent optical technique, enhanced image contrast can be gained by further analyzing subtleties in the polarization or the phase shift of the backscattered light. Now I'd like to highlight a handful of interesting areas where OCT is being used in industrial applications. These are, of course, only a small fraction of the existing and potential uses for OCT, but I hope it gives you a flavor of OCT's capabilities. Selective laser sintering is an additive manufacturing technology which uses a high-power laser to fuse particles of a metal powder, layer by layer, in order to create a 3-dimensional object. As an expensive process, reducing scrap due to defects incurred during printing is critical. Even if parts cannot be recovered while printing, it's important to scrap parts before more time and materials are expended. Defects can occur from small irregularities in the metal powder bed, and thus a real-time powder bed monitoring technology is desired. OCT can characterize the powder bed and discriminate between fused and non-fused powder, as well as measure height irregularities which can accumulate into warped parts. The OCT scanner can be attached to the recoder arm to characterize surface roughness and identify irregularities before and after a round of sintering. Or the OCT beam can be integrated in line with the processing laser beam to enable keyhole depth and porosity measurement during sintering. Another area where OCT has utility in additive manufacturing is for non-destructive tomographic imaging of translucent or semi-transparent materials like polymers. We show here how an OCT scan can be used to identify subsurface defects or voids in a PLA filament extrusion part. The XY images are reconstructed at different depths corresponding to the horizontal blue cursors in the orthogonal planes. On the left, you see a section through mostly continuous top layers, but on the right, a section through deeper layers shows that the part contains large voids in the material which are not apparent from the exterior. OCT imaging in these circumstances could be used for material and process development, quality assurance, or avoiding scrap if defects can be identified and corrected in real time. Flat panel displays have many thin, transparent, and functionalized layers stacked into a few millimeter thickness, making OCT an ideal tool for inspection. The OCT-based 3D metrology shown here is for an e-ink display, where one can clearly visualize the layer thickness, adhesion, and potentially defects. Interestingly, because OCT is also sensitive to Doppler shift, it can be used to make functional measurements, like sensing the motion of charged pigment microcapsules as they move between electrodes to change the display contents. OCT's cross-sectioning ability make it a promising tool to perform 100% inspection on thin films and coatings as an alternative to random and destructive point sampling. Some examples shown here include automotive paint or the conformal coatings used to protect printed circuit boards. In these applications, the thickness and continuity of the coating is often critical for longevity, and subsurface defects can shorten the time to failure. OCT can even detect metal corrosion below the surface of a coating. The thickness and continuity of coatings deposited on pharmaceutical tablets or capsules can affect a variety of functions, such as for timed release products. OCT is used for tablet inspection at several phases of pharmaceutical research and process development, as well as production quality control of both pills and the blister packs used to package them. I've highlighted several applications of OCT for its ability to measure thin layers on the micron to millimeter scale, but it also has some important advantages in 3D scanning and metrology of larger objects and scenes. By trading off some resolution for increased ranging depth, one can achieve a short-range LiDAR scan over distances of multiple meters using next-generation VCSEL-based swept sources. Some advantages of using swept source OCT technology include insensitivity to surface finish, which can be problematic for triangulation-based scanners, insensitivity to lighting conditions, which can be problematic for structured illumination and photographic scanners, and higher resolution and accuracy than time-of-flight laser scanners. Excelitas supplies a large catalog of swept source OCT products via its Axsun brand. These range from compact swept laser subcomponents to custom data acquisition and processing electronics to integrated imaging solutions that are adaptable in a plug-and-play fashion to a variety of application-specific scanners. Cutting-edge performance is available across several spectral ranges, providing high speed, high resolution, and long ranging depth in a way which is both cost-effective and scalable. Axsun laser products built on our core micro-optical assembly technology and MEMS tunable lasers have logged billions of operating hours and are supported by a team with decades of experience in laser and OCT system technology. Thank you for attending this virtual presentation. Please leave your virtual business card and a salesperson or applications engineer will contact you soon.